Hi everyone, welcome to video lecture on renewable energy resources. In this video, we are going to discuss the next unit, that is solar radiation and measurements. In the last video, we have discussed about what are the types of renewable energy available, what are the benefits of renewable energy, how they are better than conventional energy resources like coal, petroleum products, and other conventional energy forms. This class actually we are going to discuss about solar radiation and its measurement. So now, instead of deviating our efforts in other form of non-conventional energy, we will start focusing mainly from on solar radiation and other forms of energy. How do you convert solar energy, how much energy is reaching the earth, and how it will be extracted, what are the techniques used, and also what are the equations that are used to calculate the radiation energy that is reaching the earth. Then what happens to the inclination, geographical locations, and what about the altitude of solar devices. If you keep at some height, what is the energy released? All these things will be discussed now. Now moving on to the next slide. That is more in depth with the solar energy. The solar energy reaches the earth in the form of radiation. Radiation is an electromagnetic wave which has electric and magnetic field, and it travels at a speed of light. So this form is it's a one form of energy transfer where you don't need any medium. You don't need any medium in the sense from sun till the light reaches earth. It doesn't require any medium for energy transfer. Like if you say heat, it needs to be some liquid or solid, or you have to physically touch the heat to get transferred. But luckily the earth has a temperature at which it emits continuously radiation, and that much energy itself, radiation itself, is enough for us to survive with energy resource. So earth will receive nearly 10 power 17 joules of energy every second. So the energy what it reaches the earth may be directly used, or it may be used indirectly. Directly in the sense you take the solar radiation, use it for heating application. Indirect forms, you can generate electricity indirectly, like if you use agricultural product, say some algae cultivation, which I have discussed in the last class, or if you take say some biomass, or if you take rainwater in the dams which is collected and used to generate electricity. These are indirect forms of solar energy. Like that, we have so many direct forms, indirect forms of solar energy that is used. And this solar radiation has a lifespan of, say, some millions of years. That's why we can say that solar radiation what reaches the earth is an inexhaustible source of energy. I mean to say, the sun has a life in millions of years. Like it may be some hundreds of millions of years he will survive. Before the extent of earth, uh, we can extract, or we can use more and more number of gigawatts of power from the sun, because it's a huge quantity of renewable source of energy. But unfortunately, it has some bad drawbacks. That is, it is not continuous. That means the radiation what falls on the earth is not a continuous radiation. Sometimes cloud may come and obstruct the radiation. We know from morning 8 till say some 6 or some 7 o'clock you will get solar radiation, but the intensity in the morning is different, intensity at the afternoon is different, intensity at the evening is different. So it is not reliable. Continuously you will not get power. In between, if cloud comes, dust comes, or any other material comes in between, then it will reduce its intensity. So if intensity is reduced drastically, the power production will come down. So continuously we cannot generate. So there is a need of battery storage in order to solve this issue. So compulsory they will try to manage electrical storage means if you are converting solar radiation into electricity. But for water heating or any space heating, it is not that much problematic, because it will heat when it is at peak, when sun radiation, solar radiation is at peak, it will heat up the space. So that heat will be stored again. Heat has to be stored again. It is like electricity only. We have to store the heat in a insulated tank, then it can be utilized. And the second drawback is it uses more space in the sense, uh, say if you have to extract some kilowatt of energy using say some nuclear power plant, it hardly consumes area in acres. Maybe some 600 acres or 700 acres space may be utilized to generate a very huge amount of power. But to get the same amount of power from the sun, the space required will be more than what you can get it from the uh, nuclear or hydropower plant or any other forms of, like it may be diesel engine also. Let us take the example of diesel engine. So one diesel engine hardly takes a space of 3 feet or 4 feet, a small generator. It can power your home. But if you have to power your home with only solar energy, you need at least say some 30 or say some 60 feet square area, 60 feet square area of solar panels are required. That's why it consumes more space. It's a rough calculation, but you can understand this. So the space required by a small generator is less. That is conventional energy. If it is non-renewable like solar energy, you need to have very wide area solar panel. The radiation which comes to earth is in the form of electromagnetic waves, and that electromagnetic waves will have some wavelength, and that wavelength, how it affects the energy absorbed, because at certain band has a certain form of energy, say 0.2 to 0.4 micrometer is what the effective radiation length that will be used, or it will be extracted or can be converted from the sun. So out of this zero point 0.2 to zero point 0.4 micrometers, what we extract is 8% of UV rays and 46% of visible light and 46% of infrared light. So all these three subcategories will constitute a complete solar radiation. So solar radiation will have three constituents of electromagnetic radiation. The total band width is 0.2 to 4 micrometers. Hope you can understand. So it ranges from 0.2 to 4 micrometers. What the total bandwidth in that, UV rays also comes into picture. That is very smaller radiation, smaller wavelength radiation, and they are highly energetic. To say frequency wise, they have a very good frequency. And another band is in between visible light. After UV you have a visible light, and that comes around 46% of the visible light, and the wavelength ranges from 0.39 to 0.78 micrometers. So visible light wavelength ranges from 0.39 to 0.78 micrometers, and remaining thing is 46% infrared radiation. Infrared radiations are form of energy which is in easily extracting, which helps in easily converting into the heat energy. So infrared, actually it is emitted. Infrared rays are generally emitted by a hot body, so obviously it constitutes a major part of the bandwidth of the solar radiation. That is 46% of radiation is infrared radiation. Again, that radiation starting from 0.78 micrometer till 4 micrometers. So that whole bandwidth is infrared infrared radiation. So like this whole light energy which comes as a radiation to the earth will be utilized in different forms, and that will be converted into electrical energy or light energy or heat energy, depending on the applications. So in the next slide we will discuss about solar constant. Solar constant is a value in which gives you how much amount of energy is received in a unit time and in a unit area of sphere, so on the surface of the earth generally. Okay, next, before going to that solar constant, solar energy from the sun is released because of the fusion reactions that has been taken place very far away. That is, uh, say some 1.5 into 10 power 8 kilometers uh, along the distance. So the diameter of the earth is 1.27 kilometer, diameter of the sun is 1.39 kilometers. The distance between these two objects is 1.5 into 10 power 8 kilometers. So earth has 1 into 10 power 4, sun has dia 1 into 10 power 6 roughly. You can see the slides, so from the slides you can get the exact value. The distance between them is 1 into 10 power 8. You can see that. So because of this much distance is there, uh, the spherical shape of the sun and spherical shape of the earth uh, will make the radial direction in the sense the sun emits the rays along its radius, because it is spherical. So we assume that it emits the radiation along the radius, and because of this radial emissions, there is a small angle gets subtended by the radiation which is coming towards the earth surface. For example, if you take a plate or if you take a mirror, and if you allow the light to get reflected on some surface, then what happens? Then the parallel beam of light will go and reach the wall because the surface is flat. If that is bent, assume if that is bent, the reflected light will not be no actually it is not a it is not only of that much space. I can say that it gets reflected to many area. It gets reflected into many different space other than only the size of the mirror. But if it is concentrating mirror or parabolic type of mirror, which not parabolic actually, maybe yeah, if you consider parabolic also, it has a point of focus. At that location all beams gets converged. One point, if it is diverging, light beam also gets diverged. Similarly, if light from sun also while coming, it makes a negligible angle. That's a very small angle. It subtends a small angle of 32 minutes. That means that much small gap is the actually the light beam which passes through the earth. So it comes and falls on that. Those two beams of light will have an angle of 32 minutes. It's not like they're parallel. In fact, for calculation purpose we need not to worry about this because it is very small, negligible. As the distance is so large, we assume that radiation reaching the earth is parallel. We assume like that. That will minimize the calculation complications. And so and so and so we assume that solar radiation coming from the sun are nothing but same as a black body of temperature 5762 degree Kelvin. Black body is emitting the radiation. We clearly assume in that sense. So black body in the sense which is actually emitting the parallel beam of light, a flat surface of black body which emits the 5762 degree Kelvin of radiation. So this is what we are going to assume for simplicity. So then with this assumption we can define solar constant as it is the amount of energy which we receive on the earth in a unit time, in a unit area perpendicular to the sun, but where at mean distance from the sun. What is mean distance from the sun? During summer sun is close to earth, but during winter sun is little far away from the earth. If you don't define when is that intensity you are going to refer as a solar constant, that doesn't make any sense, uh, because it will lead to the wrong assumption. That's why we take a mean distance. At mean distance, this energy released from the sun, or we can say in the other sense energy received by the earth in unit area, that is called solar constant. And that value is, the solar constant value is 1.353 kilowatt per square meter as reported from the NASA experiments. So what actually NASA did is it took some trials in all the time of the year. Then at mean distance 1.5 into 10 power 8 kilometer distance roughly, at that time how much intensity of light is received by the earth. This 1.3 is actually a standard value, and it is not same or 100% all the time. No, it is not in that sense. It is a constant value at very particular conditions, in the sense the earth should be at exactly at that much distance from the sun, say 1.5 into 10 power 8 kilometers of distance. Then there should be a cloud free situation. Then Then there should be orientation, like how much inclination is there between sun and between the earth. These all matters in the constant value if you want to get that value. But this 1.353 kilowatt is roughly a value which is measured outside the atmosphere. When it passes through the atmosphere, its energy will be little less. So on the earth, it is difficult, very difficult to measure 1.353 kilowatt of energy in a space, small space of 1 meter square. And we can see that this value varies as earth rotates around the sun in its circular orbit. What it says, because earth is rotating and sun light which is falling on the earth will be different at different seasons, summer, winter and rainy season. And this variation comes because of the change in its distance between the earth and sun. So because of the distance, change in distance between the earth and sun. And this 1.353 kilowatt per square meter is expressed in different units. Say it is nothing but it is equal to 116.5 Langlays per hour, or 1165 kilocalories per square meter per hour, or it can be represented as 429.2 BTU per square feet per hour. So these are some of the units represented globally. You can refer textbook, or just let me know. I will share the details of these things further if you require. So I have the textbook called GD Rai, Non-Conventional Energy Sources by GD Rai. If you refer this textbook, you will get the complete details of other forms of units represented by the NASA. Then next what we can see is what happens is, if you have to calculate intensity of radiation at any point of time, assume maybe in summer or winter. So at some point of the day, if you want to if you want to measure the intensity of radiation, there is an equation. So this is equation is I by I, this is I by ISE. SSE is solar constant. This is standard value, that is 1.353. So I by ISC is equal to 1.033 cos 360 into n minus 2 by 365. So this is the equation to calculate the intensity of solar radiation coming towards on the earth on some day of the year, where n is the number of day in a year. For example, if it is March, then we have to March 1st or something, if that is the day, then we have to consider it how many number of days in January plus number of days in February plus the date of the month in the March. Like that we should enter, and we can get the intensity of the radiation I at some part of the time of the year, any day. Next in here we have a table. What we can see from this table is last video. In the last video I have discussed about the how many bandwidth of the radiation reaching the earth. Infrared is there, then visible light is there, then ultraviolet light is there. 0 to 0.38 is mainly the region of ultraviolet light, and it is only 7% or 8% sometimes, so plus or minus 1% is there. So only 8% or 7% of the total energy of the radiation which is coming to earth is uh, because of the ultraviolet radiation. And because of that bandwidth, you will get 95 watt per square meter of energy. And with visible light, which constitutes 47.3%, we can see there is 640 watt of energy in a small area of 1 meter square. So the unit is watt per meter square. 640 watts of energy is falling on the ground or on the surface of the earth for an area of 1 meter square, and that is because of the visible light. Then we have 45%, or roughly both are 40, 46, 46. We can consider what I have explained in the last class. And same as 1618 watts of energy per meter square of space. That much energy is getting absorbed by the earth. And that is in infrared radiation, and that infrared radiation bandwidth is from 0.78 till 4. Below that we have a graph that shows a spectral distribution of solar radiation. And in that graph what we can observe is the x-axis wavelength is there, y-axis uh, how much energy is received from the sun is mentioned. So the unit is watt per meter square, micrometer per micrometer. That means each wavelength of the radiation which is coming to earth is contributing some part of the energy. For example, not all bandwidth has the same energy. Some bandwidth has more energy, some bandwidth has less energy. So what we can see is the bandwidth at 0.48, nearly 0.48 micrometers, has a maximum energy output of 2 kilowatt per meter square. It's a great value. See, in one small area of 2 meter square we are getting 1 meter square, in a small area of 1 meter square we are getting 2 kilowatt of energy. 2 kilowatt in the sense 2000 watt, nearly exact value is 2074 watt per meter square. You can refer the textbook for clear further details. So what you have understood is different wavelength contribute to different energy content of the solar radiation. So that much radiation is coming to earth, but particular wavelength has an effect on releasing more energy to the earth. So this is what we can conclude from this slide. Yeah, in this slide we can see how much radiation will reach the earth. What type of radiation will reach the earth? Till now we have discussed the radiation coming to earth, but after coming to earth it has to pass through atmosphere. Atmosphere is a layer of air above the earth surface, and it is not just one component present in the atmosphere. The thickness of the atmosphere is different at different heights, and also the constituents of the atmosphere is also different at different places. Say in some place there may be dense smoke, in some places there may be a dense cloud, or in some places there may be a dense dust storm coming. Then maybe moisture content, heavy moisture, fog. Atmosphere is totally a different scenario. It is having different components in it. So it it actually faces an obstacle to the light reaching the earth surface. At all, earth will receive nearly 1.3 kilowatt of energy for a unit space of 1 meter square, and this after reaching the earth atmosphere, when it tries to come and reach the earth surface or the sand or ground of the earth, it will lose some of its energy content, because as you can see in the slide, some part of the energy is reflected back into the space. So it will get reflected back into the space. That means outside the earth, it will get reflected back to outside the earth, away from the earth into the space. Especially this is by the clouds which are present on the earth surface, that is on the atmospheric layer. So these clouds reflects the light energy back to the space. So further, this reflection occurs by different component. As I told, there is one more layer called ozone. Ozone is an oxygen layer, and this layer uh, reflects most of the ultraviolet region of the solar radiation. Ultraviolet band, that what I have already told, 0 to 0.38, 0 to 0.38 uh, micrometer of wavelength radiation gets reflected by the uh, ozone layer. It will get reflected or absorbed by the ozone layer, and that will not reach the earth. That will not reach the earth. That means some part of the energy is lost, and the remaining part of the energy is absorbed by the molecules of moisture present in the air. So carbon dioxide also absorbs some of the energy of the infrared radiation, that is again part of solar radiation, and moisture content or water vapor present in the atmosphere absorbs the solar radiation which is coming into the earth, where predominantly infrared region is absorbed. Infrared region constitutes 46% of the energy, you should remember. So this much of energy is absorbed by the solar radiation coming to the earth. Later, so finally we are left with only some 50% or 60% or 80% of the radiation, depending on the how much cloud is there, how much ozone layer is present in that location. So based on that, it affects the solar radiation reaching the earth. So because of all these things, the direct beam of light, so you can see in the slide, there is a sun here, and the sun is passing the radiation beams into the earth. Here we have a panel which actually extracts the solar energy, and we have plant here which is just a simple example of receiving both two types of radiation, sorry, both the radiation, that is direct, you can see direct radiation, and also diffused radiation. So what is direct radiation? So when sun emits the radiation without reflection, without scattering, this beam of light slowly comes and reaches the ground. So you can see this is the ground. So direct beam of light will straight away come and fall onto the ground. You can see these solid arrows, but you have also dotted lines. These dotted lines comes because of reflection. So direct beam, after hitting some part of the ground, it gets reflected back to some absorber, another absorber. So if that type of light is there, that is called diffused radiation. Very important concept, because the energy received by the ground level or at the ground level on the surface of the earth is summation of both direct radiation and diffused radiation. So you can see that total radiation received is direct radiation plus diffused radiation. So direct radiation is what I have shown here. So directly it hits the surface beam, light beam. But diffused radiation is, see, clouds. It hits the cloud, then it hits the air molecules, then there are aerosols, or we can say some water vapor droplets. Those things will reflect the radiation, that is called diffused radiation. So these both constitutes for the total radiation received by the earth, and this total radiation received is called insolation. So on horizontal surface, if you consider on the earth any horizontal surface of some area, then that energy received by that radiation is called insolation, total radiation or insolation. And why it is important to study this is, during cloudy atmosphere, so some percentage of diffused radiation will be there, and it can reach up to 20 to maximum 50% also. That much of energy will be in the form of diffused radiation, because if sun is abstracted by a cloud, if sun is covered by a cloud, then there is no chance you can see the direct radiation. That is why if direct radiation are blocked, then the radiation what we see is diffused radiation, and it can reach generally 20 to 50% of the total radiation. In this graph we can see variation of spectral beam with respect to wavelength. See, I have told energy comes to earth is roughly 1.3 kilowatt per meter square at the surface of the atmosphere, but at the surface of the ground, or we can say at sea level, that value is only 1 kilowatt. So that means instead of taking it as 1.3 kilowatt, we have to take it as 1 kilowatt if you are measuring at the sea level, because that much of energy has been absorbed by the atmosphere. What you can imagine from this is, radiation has energy which will be absorbed by the atmosphere. Finally we will get not 1.3, we will get only 1 kilowatt of energy per unit area. And if you go 1000 kilometers 1 kilometer above the sea level, then the energy content what earth will receive at the any solar device will receive is 1.05 kilowatt per meter square. And if you move a little bit up above some mountain value, then the energy content received by the earth is 1.1 kilowatt per meter square. These units will be in terms of a unit area, that is meter square. But atmosphere, the value will be 1.353 kilowatt per meter square. That's why we define, as already we have defined in the last slide here. So at air mass 1 we will get energy of 1 kilowatt, but if you go up high above the atmosphere, somewhere here the air mass is 0. Air mass is 0 because the distance of light traveled off the above the surface of atmosphere at the starting point of the atmosphere, then it is 0. am is 0, that is air mass is 0, and air mass is 1 for the surface level of the sea on the earth. That is why what we can see is the energy is lost during its travel. So we can say energy is lost during its travel. So in this slide we can see say different wavelength and what is the energy spectrum which will give the energy content. So this band 0.4 to 0.8 will have peak energy content, that is somewhere around 2 kilowatt of energy content in this band. Before 0.4 the radiation has very less energy content. After 0.8 till say some 4, that is infrared region, that infrared region, visible region, and say some ultraviolet region, you can see the bandwidth is mentioned here. So these three different bandwidth will release lot of energy content to the solar devices on the ground, and that value is shown in the graph. Here there are 1 2 3 4 curves are there. These four curves, these two are diffused radiation curve, and these two are total radiation curve. So what you can get from this is at sea level, the energy content whatever we received is only 1.5 kilowatt, but at outside the atmosphere, you can see this curve am0 means air mass 0 at surface of the atmosphere, andre that means before reaching the ground. So it is just starting layer of the atmosphere. At that point visible light has a energy density of nearly 2.5, nearly maybe between 2.3 I can say kilowatt of energy per unit space, that is per meter square. So like that, if you want to know the losses, that is called it is very important, atmospheric transmission factor. You should remember atmospheric transmission factor. So what you can do is, so if this is the curve which atmosphere is getting, and if this is the curve what ground is getting, you take the ratio of the areas, you take the ratio of areas of the curve. So area under this lower curve divided by area under the higher curve. If you divide, you will get the transmission factor, and this transmission factor is 0.633 for m is equal to 1, for m is equal to 1 am, that is air mass is equal to 1. Then it is 0.276 for air mass 5. If air mass is 5, then it is 0. So that means if air mass is 1, you will get a transmission factor of 0.633. like that, say at some distance, when this inclination is very high, at that point air mass is 5, and you will get a light energy of some unit, but transmission factor will be only 27%, that is 0.276. These values you can get it from the textbook. Just you understand from this graph that energy content at a 3 different radiation is different, and in that visible light has more energy content. In that again the atmosphere absorbs this much of energy, that is the difference between these two curves. That is why you will get a term called transmission factor. So you will get a term called transmission factor, ratio of this area divided by total area of the second curve or highest curve. These are the absorption by different components, H2, H2, like all these points at a different frequency, light has been absorbed, light in the sense radiation. And here you have a diffused radiation component, very low intensity, so they have only 0.5 kilowatt of energy per meter square. Okay. like that. This is about variation of energy density with respect to wavelength, or we can say spectral variation of energy outside the atmosphere and also at the ground level.